Ladies and gentlemen, please join me in welcoming our 2018 Van Horn lecturer from Caltech, Professor Harry Atwater. It is a really great pleasure to have him here. I have to think really hard to having ever seen this lecture hall filled up to the last seat. So that's pretty remarkable already. I would like to say a few words about the background of the Van Horn lecture series right now, and then hand over to Professor French, who will introduce Professor Atwater. The name Van Horn is omnipresent in our department and on campus. Everybody knows the Van Horn Library. Most of us know the Van Horn Field, and there are other little landmarks that remind of Frank Van Horn, who was a founding father of our department at around 1900. And Frank Van Horn was not a material scientist, he was a geologist. And he collected minerals, some of them apparently precious. The Cleveland Museum of Art has an exhibition of them. And he and his wife, in those years, were also known for his activities in sport, and they made a donation, which is the foundation for our Van Horn scholarships, and they had a son with the name Kent Van Horn. And this Kent Van Horn is a Case alum who is really a metallurgist. He graduated in 1926 from Case and then moved on for doctoral studies into a country far, far away. It's called Germany. It has a lovely town called Heidelberg, where he enjoyed himself for a while, and then returned and joined Alcoa as physical metallurgist. And his career there was, I think, sort of typical. He at first was involved in practical engineering problems, but then moved up into the management, and it was soon recognized that he had extraordinary talents there. And he then later moved to a little town near Pittsburgh and actually became the corporate vice president of Alcoa. And it is this Kent Van Horn who, with a further donation, augmented the initial donation to the point that then established the Van Horn lectures. And Professor Atwater is actually our 45th Van Horn lecturer. And that's nearly a round number and shows what a long tradition this has. If you get a chance, take a look in the Van Horn Library. There will be a board with plaques with all the former speakers, and that reads like the who is who in material science and physical metallurgy. And in fact, these Van Horn lecturers are selected by the department's faculty in a very careful way. So every year we screen the field for eminent scholars, and we select Van Horn lecturers, of course, under criteria that relates to their scientific work, their publications, but also their ability to talk to students. And talking to students is a very essential component of this event. So at times when Professor Atwater is not giving us a lecture, he will be most likely in the Van Horn Library talking to some of our students. And that's a very important mission, and I encourage everybody to participate in these stimulating discussions. Now, before I hand over to Professor French, I would like to make you aware of one important schedule item. We would have normally had 3 lectures in the same location at the same time. However, tomorrow afternoon we have the school's award meeting, and therefore we cannot have this time. Tomorrow's lecture will be already at 11 o'clock in the morning in Sears 356. Can somebody please confirm that? Yeah. Sears 356, 11 o'clock in the morning. The Sears building is the adjacent gray building, adjacent to the North Hall. I hope to see you all there. And at this point, I would like to hand over to Professor French to introduce Professor Atwater.
So it's our pleasure to have Harry Atwater here. I thought I would start actually sort of early on in some of his activities, just because I think that he can actually feel quite comfortable. It's 33 degrees out. Of course, you know, we pay a lot of attention in solar to the weather and the natural resources. And it's 33 degrees out and it's snowing, but he grew up in State College, Pennsylvania. Okay, he also said he fled there at 17, but still he grew up there. Okay, so therefore I know it's not necessarily Pasadena weather here, but it can make you feel familiar. Good things like that. Yeah. And then after that, he and I overlapped at MIT a bit. He was in EE and worked with Hank Smith. But I really liked his actual thesis title because it's ion beam enhanced grain growth, just in general. But if you go look, it's well, germanium and silicon, I would have expected that, and gold. Also, metallization on semiconductors, or some other things are also in there. It seems like the second to last chapter was titled something like, and then also, I don't remember exactly the title, but so like an extra chapter of other things too. And we were talking yesterday about how, let's see, my advisor and his both emphasize the importance of having lots of ideas, and if someone steals your idea, don't worry about that, because that means they have a paucity of ideas and they won't actually get very far with that, and you can just crank up more ideas. But that's almost one of the most important things that we have. It's sort of interesting because over the years then, well, you actually went to Caltech pretty quickly, straight away, and you've been there a long time. But you've changed the place an awful lot too, because I like the idea of having JCamp, which is the title of the topic here, Joint Center for Photosynthesis, Joint Center for Artificial Photosynthesis, which I think this might be the first time I've met someone whose actual funded project is a line item in the congressional budget. Not just to the program officers, you know. So like, I see, okay, I haven't really thought of something in that dimension yet. He's the Howard Hughes Professor of Applied Physics and Material Science at Caltech. And it really has been these two themes that I always think of for the work that you've done with light matter interactions and nanophotonic materials, plasmonics, things like that, and solar energy conversion. And we've overlapped a lot in the photovoltaic side of things. And it was sort of like one of the things that gave us some pause here was a couple of years ago when a company sent us some Alta devices, single junction gallium arsenide solar cells, to evaluate how good they are and how long would they last. Do they degrade too fast? They were very concerned. Lucky for me, I can say, oh, actually they performed well and they didn't degrade too fast. And I was like, oh, phew. You know, because I knew that they had a good airplay. Sometimes reality and degradation, you know, doesn't really work that way and stuff. He's a member of the National Academy, co-founder of that Alta Devices case, which still has the record for the most efficient single junction device. And then, for example, now, many years ago, as president of the MRS, and a whole bunch of other sort of accolades along the way. But I think really one of the most interesting things is that if I think of the work that you've done, I almost think more of all of the people, the progeny, who have come from your group and gone on and done really cool things. And I think that that might be the best compliment to any faculty member. And so we look forward to your talk today on fueling human progress with sunlight.
Okay, yeah. Thanks very much, Roger and Frank, for the very gracious introduction. So I want to tell you today about some work that I'm very passionate about, and I have been ever since I entered college, because at the time that I entered college was shortly after the time, or sort of just during the time of the first energy crisis in the United States, which Jimmy Carter declared to be the moral equivalent of war. And so we'll see a number of interesting things, and I want to tell you a couple of stories today. But I should also note that none of this is done alone, and it's all done together with a group of talented students and postdocs and senior collaborators from Caltech and elsewhere. I'll just note here the students who have been involved in this, as well as my senior colleague Nate Lewis at Caltech. And so this perspective on the Earth where you see the sun, I think it reminds us of a couple of things. For one thing, you can see, first of all, that the sun does indeed shine on all the Earth, and it's a very democratic energy source. It provides sunlight to the entire world. It also reminds us that the Earth is quite finite. It's quite large, but finite. And you can also see this thin blue line that shows you the atmosphere here that is really a tiny fraction of the Earth's diameter and is really quite precious and important to our way of life. So I'm going to spend a little bit of time talking about carbon dioxide, and at the end of my talk I'll get into generation of fuels. But you may have heard of this guy who started a little software company, and in 2015, right at the time of the COP21 climate meeting in Paris of international leaders, published a white paper called Energy Innovation, Why We Need It and How to Get It. And he helped to form a consortium of high net worth individuals who are providing $1 billion worth of private capital through what's called Breakthrough Energy Ventures, because he felt that government wasn't doing enough and that the private sector needed to step up, and they're going to begin making investments in across not only solar but a broad array of zero carbon and negative carbon technologies. And so why is this important? The units are hard to see here, but this is grams of CO2 per kilowatt hour, and it ranges from 0 to 600, and the time axis is from 1990 to 2050. So what you can see here are three curves. They're colored curves. This greenish one is the 6-degree scenario. The orange, reddish one is the 4-degree scenario, and the blue one is the 2-degree scenario. That's the one that the world's leaders agreed to. In fact, they agreed to a degree and a half in Paris, and so the 2-degree scenario basically tells you how the grams of CO2 per kilowatt hour has to ramp down from right now. This is where we are right now. So it's telling you this has to happen immediately in order for us to meet the climate objectives that were set in Paris. Moreover, these dotted lines here, these dashed lines, are an indicator as we bring on new energy sources, what the carbon intensity of the new energy sources has to be consistent with this line. Of course, it has to be lower because we have the legacy sources, which are still more carbon emitting. And you can see here, this looks like a nearly impossible task. So what it really means is that we have to advance technology, you have to do it relatively urgently, and we also have to seek out ways to not only reduce or mitigate the emission of CO2, we have to find ways to transform CO2, ultimately to completely close the carbon cycle so that we make carbon be a renewable resource. That's going to be a real challenge for the next generation, for those of you students who are looking for a hard problem to set your careers against. Okay, so there's another, we have some reasons for optimism. This is, back when I was a graduate student, this is where the price of solar photovoltaic panels was, up in the $100 per watt range. And the cumulative output of manufactured capacity of solar panels was a few megawatts per year worldwide. And to give you an idea, on a typical campus nowadays, for example at Caltech, we have about 5 megawatts of solar deployed on the campus. And you can see here this exponential cost decline. In fact, it's not really some people refer to this as a Moore's law curve for photovoltaics. I resist that association because this is only 2 orders of magnitude, or a little more than 2 orders of magnitude reduction in price, which is not quite as spectacular as the cost per bit reduction in computing, but it's what was needed to cause this huge capacity expansion to reach the point where solar as it is now today, is starting to become competitive. And so this curve is a little bit dated, and it stops here at a panel price of about 60 cents a watt in 2015. And what we'll see actually is that today the solar landscape is even more favorable. The price drop, if you haven't checked your Google feed recently, you're not up to date on the price of photovoltaics. It's dropping that fast. In fact, when I was in China earlier, or late last year, there was an expectation that the price of modules, manufactured modules, would go to 20 to 25 cents a watt. And that's a really remarkable drop. So it's dropping even by factors of a third or a half in year over year. So today, the photovoltaics industry is the world's largest optoelectronics industry. It's now surpassed the flat panel display industry in terms of industry turnover. It's much bigger than, for example, the solid-state lighting LED business, bigger than all of the other laser communications and businesses. 90% of it consists of crystalline silicon. This was really the first technology that was commercialized. It's the incumbent, and because it developed a very vertically integrated supply chain with manufacturing, distribution, marketing, equipment vendors, and so forth, it's now reaching the stage of being quite a mature industry. There are about 60 gigawatts worldwide of photovoltaic manufacturing capacity. And for a while, over the last few years, there was a dip in the there was an overcapacity build worldwide, largely in China, but now the demand has caught up, and we're now the actual production is starting to match the capacity again. So record silicon cells, the record champion cell has an efficiency of 26.6%, and that's now reaching the point where the cell efficiency is starting to plateau, but it's nonetheless a remarkable achievement. With one of the advantages of having such a large manufacturing industry is that there's so many cycles of learning and so much knowledge accumulation that you really learn how to optimize the technology. Commercial cell efficiencies are in the range of, and module efficiencies are usually separated by 1 or 2 percentage points in the 19 to 21% range, and the module cost now is, at the time I wrote this slide, was about 35 cents a watt. This is a large modern manufacturing facility in Singapore, and there are facilities like this all over the world, a lot of them in China, but not only. In fact, you may know that Tesla and Solar City are building a gigawatt scale factory in upstate New York, actually, for the Panasonic silicon heterojunction cell process. So I want to note a couple of things. We've seen this remarkable insertion of photovoltaics. For example, in California, I'm proud to tell you that we have the world's largest fraction of electricity generated by solar energy anywhere in the world, higher than Germany, actually. It's a little more than 10%. And it's now reaching the point where on some days in the late spring that are very sunny, where the price of solar electricity goes to zero. And in fact, the photovoltaics has to be curtailed because it's too difficult to spin down the other baseload reserve sources. And so that illustrates the real problem of solar variability. As you start adding more and more solar into the grid, not only the predictable solar variability, which is predictably intermittent on a daily basis, so day-night, that's compensated for somewhat by the fact that it's somewhat, in most locations, counter-cyclical in the diurnal cycle with wind, but not completely, and so there's a real issue with storage and the intermittency. In late last November, I gave a lecture in the Nobel Symposium in Gothenburg in Sweden, and so I decided to look up the seasonal solar variability in Gothenburg, which is at 57 degrees latitude, and they have a factor of 10 variation in the solar flux from winter to summer. And in fact, the way they buffer their energy supply in Sweden is by pumping water in Norway and then discharging the water from the hydro fields in the fjords of Norway. But there's a more serious issue, which is that, as for example, in any of the electricity markets in the United States or anywhere in the world, what we can see is that as you add more solar capacity as a percentage, going from a few percent out to say more than 30%, the effective cost of solar, the cost that solar has to be at in order to be competitive on an delivered energy basis has to drop dramatically. As it goes, when you first introduce solar into the grid, there's not that much need for storage because it's a tiny fraction of the total capacity. As the capacity grows, then you really need to have a significant growth in storage, and so therefore the cost of solar has to drop to accommodate the cost of the storage. Whether that be lithium-ion batteries or pumped hydro or sodium sulfur large-scale batteries. And so this is a real challenge, and there's therefore sort of a value deflation that necessarily accompanies the increase of the penetration in the market. So as we look for ways to go past into the next era for solar energy, what we need to focus on is what we call dispatchable energy. We don't want energy to be unavailable at night. We expect to be able to plug in our iPhones and charge them up overnight, or have power to read at night. So you want dispatchable energy. You want it to be available when you're ready to use it day or night. So in order to do that, we need to have photovoltaics go to a cost basis which is so low that we can afford to pay for the storage. Those of you who are working on lithium-ion batteries and other electrochemical storage technologies, this also is a very, very important part of the overall energy R&D landscape. And so I look forward to hearing about your work as well, because we urgently need it. But there's another opportunity I'm going to talk about today, which is the direct synthesis of chemical fuels from sunlight. So using sunlight and storing it indefinitely in the form of chemical bonds. And this is something where there is no manufacturing industry. When I was a graduate student, there was essentially no manufacturing industry for photovoltaics. Now we have this worldwide industry. It's one of the largest industries, manufacturing industries. Right now, there's no manufacturing industry for this, but it's really interesting from my point of view, because we're now at the point where we have prototype devices that look like the prototypes we had of photovoltaics back in 1975. So I want to start a little bit with some fundamentals and ask the question, not why is a solar cell 26% efficient, but why is it not 93% efficient? I mean, we're entitled, based on just the Carnot efficiency of a thermal engine operating between the hot side and the sun and the cold side on the earth, to that kind of efficiency. So why is it that we don't have such efficiencies available to us? Well, there are a number of reasons. One, there are some very fundamental ones, and they have to do, and so here is where this green bar reflects the sort of current efficiency limits. And there are some important, what I'll call fundamental thermodynamic principles that are at work that define the limits to solar conversion efficiency. Some of them have to do with entropy. One of the things I'm going to try to, for a department here that is really steeped in and leading in the area of phase transformations and materials, what I'm going to try to leave you with today is the idea that energy conversion between light and charge carriers has a fundamental thermodynamic basis. And so I'm going to be talking about the free energy of solar energy and how we can utilize this as a design principle. There are various entropy losses associated with the angular distribution of light, incomplete light trapping, and radiative efficiency. I'll talk more about those. A very big one is the thermalization of photons. This light blue bar refers to the fact that in a semiconductor with a band gap like this, if the photon exceeds the band gap energy, a lot of that photon energy is wasted as the hot carriers relax by electron-phonon coupling mechanisms, thermalize down to the band edge. And then the maximum voltage we can get out is less than the band gap, and we'll talk about why that is. But it's essentially due to the splitting of the electrochemical potential of the electrons and the holes. We call that the quasi-Fermi level in electrical engineering, but it's really nothing more than a chemical potential, electrochemical potential for the electrons and the holes. So that also is rooted in a thermodynamic basis. So we're among material scientists, so we're allowed to consult a philosopher here. This is, of course, Arno Sommerfeld, who gave us the first model of the atom, who opined that thermodynamics is a funny subject. the first time, and this is for the students and of course the faculty, the first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it except for one or two small points. The third time you go through it, you know you don't understand it, but by that time you're so used to it, it doesn't bother you anymore. Many of us have struggled with thermodynamics. It's an incredibly powerful theory, and even Einstein regarded it as being more powerful and fundamental than quantum mechanics. So I want to spend a little bit of time talking about limiting efficiency models for solar energy. Probably the most important one is the one that was given to us as a radiative flux balance model by William Shockley and Hans Joachim Queisser. Shockley, of course, was the inventor of the transistor and won the Nobel Prize for understanding the charge carrier dynamics and the ambipolar charge transport in semiconductors. And they pictured the operation of a solar cell as being not a closed system, but one that's operating with a radiative flux balance between sunlight, absorbed light from the sun, and in an ideal solar cell, which was completely free of defects, the only mode of carrier recombination is by radiative emission. In other words, a solar cell should be just as luminescent as the laser pointer that I'm pointing at the screen right now. So that fundamentally, with a solar cell operating in steady state in a perfect ideal absorber material, this radiative flux balance between absorption and emission defines the conditions of operation that lead to the maximum efficiency. Now, we can think about this in a sort of energy or enthalpy basis because we have a level diagram. We have a ground state and an excited state, a valence band or a conduction band, and we're photoexciting carriers from the filled states to the empty states in a semiconductor. So there's a clear sort of diagrammatic basis for the absorption of a photon, excitation of a carrier from the valence band to the conduction band, and the inverse recombination process that leads to carrier radiative emission. But there's another important way of looking at this, which is that photons actually have an entropy as well. And this turns out to be an important aspect of thinking about efficiency limits for solar energy. So in fact, what we care about is not the enthalpy ultimately, but the Helmholtz free energy. So the enthalpy minus the entropy gives us effectively the photon energy minus the this is often a configurational entropy that defines the maximum voltage that I can get to. In a good solar cell, the voltage is really the premier parameter, the coin of the realm, because a good solar cell should also even before it gets to be a great solar cell, should be able to absorb most of the sunlight and collect the photocurrent. So it's so it's the voltage that defines solar cells. So how do we view this? So the way to view this is that the voltage, for students that are not used to thinking about voltages in a sort of thermodynamic term, you can think about it this way, that if effectively we have a steady state system, we are absorbing and emitting light, and then as we introduce non-ideal processes, we have sources of excessive recombination or entropy loss. Losses due to entropy gains, but thermodynamic losses due to entropy. And ultimately, it's the flux balance between the absorption of sunlight, the necessary emission, and these non-ideal entropic loss processes that defines the potential or the water level, and in this fluidic analogy, the voltage. So in a semiconductor, the things that affect this are the radiative efficiency, the extent to which a material is luminescent or radiative rather than non-radiative in its recombination. In fact, we can regard the conversion of a material from luminescent to non-luminescent, or the difference between two materials that are luminescent and non-luminescent, as being sort of a spectral conversion. You can think of it that way. Also, another important point is that energy coming from the sun on a sunny day is coming from the sun to your eye or to your solar cell with a angular distribution or a collimation that is almost the same as the laser pointer that I'm pointing at the screen right now. It's extremely narrow, extremely parallel illumination. When we have sunlight absorbed in the solar cell generating charge carriers, giving rise to this radiative emission, the radiative emission is now isotropic. So we've increased the number of photon modes, and the number of directions, which is equal to the number of modes in a sort of ray optic view. And that necessarily accords with the increase in entropy. So simply the change in the directional distribution of sunlight actually results in a voltage loss. It's a very fundamental thing. You can fight against it, and we've actually done experiments that fight against it in a subtle way, but it's a pretty, so it illustrates this feature. And I don't want to flood people with equations, just to let you know that there is a solid basis for this kind of picture in terms of the change in the angular distribution, incomplete light trapping, and the lack of radiative departure from 100% radiative efficiency. And these are described in a paper we wrote a few years ago looking at high efficiency photovoltaics. So I want to say a little bit about materials. So this is a nice paper from my friend Albert Pohlmann that gives a sort of taxonomy of a chart showing the normalized current density versus the normalized voltage times the fill factor. The fill factor is this parameter that relates the squareness of the diode IV curve of a solar cell, because voltage times current is power, so it's an expression of the power efficiency of a solar cell, because the more square this curve is, the more power you get for a given operating point. So this is essentially a figure of merit diagram for all the materials that have ever been explored beyond the laboratory R&D level for photovoltaics. They range from, say, quantum dots to nanocrystalline silicon, dye solar cells, CZTS alloys, organic PV, perovskite, CIGS, indium phosphide, gallium arsenide, silicon, cadmium telluride. And so what you can see is there are three categories. There are things that reach above 75% in the voltage and the current, things that reach between 50 and 75%, the green band here, and things in the pink band that are less than 50% on both the voltage, or either the voltage or the current. So obviously we would like to be up here. And you can see there are several materials that are quite privileged in this regard. One is crystalline silicon. We have these incredible number of cycles of learning that have come through manufacturing. And you can see that that has resulted in silicon getting almost an optimal photocurrent density. But it's still a little ways away from the voltage limits. So it means there's still work to be done. And you can see here, this is the material that I fixated on when everybody was starting to work on silicon. I asked the question, why is it that we couldn't make good solar cells in gallium arsenide? And the answer is we can make the best solar cells in gallium arsenide. And we worked on a process to do this in a way that is manufacturable. And the reason that the best solar cells have this characteristic has to do with this sort of, if you like, a conceptual reference frame shift or paradigm shift. If we think about probably many of you came into this room thinking about a solar cell as being a semiconductor that absorbs light, that separates the charge carriers across some potential, and therefore converts them to a DC power. And that, in fact, is the sort of what I call the old physics of a solar cell. The new physics is that if we work with a material that is sufficiently luminescent, and we trap it inside a material between a mirror, a highly reflecting mirror with reflectivity close to 1, and we have a radiative efficiency, in other words, conversion between photons and electrons and holes back to photons inside the material, approaching 100%. And in gallium arsenide, that number can be 99.9%, actually. What that means is that we can have more than 100 luminescence recycling events where carriers recombined, re-emit photons inside the material, recombine, re-emit, recombine, re-emit, more than 100 times. What that means is that you end up with a very dense gas of photons and electrons here due to this recycling process relative to this process where the radiative efficiency is not high. That necessarily means that carrier density, for those of you who understand semiconductor physics, then you know that that means the quasi-Fermi level separation and the voltage will be higher. So there's a real connection between materials that are luminescent or good LEDs and good solar cells. So we started a company, my collaborator Eli Yablanovich and I, in which we worked to develop a process to remove thin layers of single crystal gallium arsenide from wafers. So the old technology is, and the current technology for silicon photovoltaics is to make solar cells on wafers. So we developed a process for peeling off the solar cells using a process that's very much like peeling Post-its from a Post-it note. It involves using a sacrificial etch process to etch away an aluminum gallium arsenide layer that yields a single crystal, and in fact it's held in compressive mechanical stress, as I was talking about with you, Frank, earlier, by lamination onto a metal backplate so that when I flex it, it doesn't crack, and it's very lightweight and flexible. This is a 27% efficient solar cell. This is more efficient than the world's record silicon solar cell. So you can see it there. So the total semiconductor thickness is 1.4 microns thick. So the laminate thickness is dominated by the plastic that's there to keep the fingerprints off it. You can see here also, this is if you now series and parallel connect in a sort of module format, you can see how cells are assembled into modules in the same lightweight and flexible. Don't bend it too far, but you can see that it's very flexible, and that actually is quite powerful in terms of some of the applications where this has been used. And because of this luminescence recycling, we were able to reach record voltages. So the currents were very similar to other gallium arsenide solar cells, but the record voltages led to world record efficiencies for single junction and dual junction cells. And just about a month and a half ago, we set a world record for modules, the world's first 25% efficient module, one sun module. So this is all being done by a company called Alta Devices. It's in Santa Clara and Sunnyvale, California. And one of the interesting features about this is because the material is such a highly luminescent and builds up voltage at low illumination levels, is it operates at nearly maximum voltage under indoor lighting conditions. So you can actually generate high enough voltages to power, for example, sensors and devices indoors. So this is myself and Eli, very happy having founded a nice company in Silicon Valley and showing a first module. This is the large MOCVD machine and the CEO standing in front of it. He doesn't look quite as happy as because he has to run the company. But over the course of about 10 years, we went from technology development of things that we made in our lab at the square centimeter level to the process development, to setting prototype records with prototype cells, and then began the hard work of building the manufacturing infrastructure and manufacturing ramp. At some point, the VCs became impatient. We sold the company to a larger manufacturing company, and now it's entering production this year, and we're now at several megawatts of production. That's tiny compared to a silicon production, but it's large for the gallium arsenide production. And part of that had to be because we had, over this 10-year time frame, to develop many novel processes that are used to make these kinds of solar cells. So this illustrates one of the application areas. This is the wing of an electric-powered airplane. And so Alta cells have been found, in fact, there are a number of very rapidly expanding markets where these are being deployed. In fact, Alta is selling everything it can make at the moment to these markets that are growing faster than it can accommodate them, on electric-powered airplanes, UAVs, mobile devices. We just signed a JV with Audi to work on. Here's an interesting lesson I was schooled in by a Toyota engineer recently, that the average Japanese worker drives 24 kilometers per day to work. And if you had a car sitting in the parking lot, and most of them park outside apparently, with 2 meters of photovoltaics, a meter on the roof and a meter on the hood, that produces enough electricity to drive the car 31 kilometers a day. So you could think now about an indefinitely non-recharged car that simply recharges directly from the sun. We normally have thought it would be sort of ridiculous to put PV on a car. I think Roger and I would have agreed on that about 10 years ago. But it's now starting to look like it might be a sensible thing to do. Anyway, so that because of the fact that this technology came along and emerged a couple of decades later. Of course, we're playing catch up to the silicon world that has now commoditized photovoltaics. This technology has found new markets, but this is what we'd really like to be able to do is to find how we could go into the next challenge for photovoltaics. And one that many people in the community see is what would be the beyond silicon module photovoltaics technology that could go to the next plateau where efficiencies would go above 30% on a flat plate basis. And there are a number of contenders in this arena. One that is being worked on very widely is to put thin film perovskite solar cells, solution process perovskite cells on top of silicon modules. There are various tandems based on the copper indium gallium selenide technology. And in this case, both the top and bottom cell of a tandem could be made using these chalcogenide materials. 3-5 tandems are another obvious possibility, in fact, ones that we've already worked on. But they require some game-changing event to occur that overcomes the cost disadvantage, even though they have a clear efficiency advantage. And what I'm going to tell you about today is what we think is something that might be able to change that game, and that's something called a luminescent solar concentrator. And a luminescent solar concentrator is a structure that allows you to concentrate diffuse light. As I'll explain, this is another feature that is related to photon entropy, and it does not violate the brightness theorem or any laws of optics. So the tandem luminescent solar concentrator that is, we think, a very interesting concept, starts with a silicon cell and module as the base absorber for the red and infrared portion of the solar spectrum. And it features now a structure that consists of a polymer waveguide. That polymer waveguide is now loaded with semiconductor quantum dots, the same kind of quantum dots that have been made by the quantum dot chemists for the last 20 years and are now, for example, in your Samsung quantum dot TVs. So it's another technology that has emerged from the research lab during our, at least for the people sitting in the front, during our careers, and is now going into the commercial arena. And so this is now it's now commercially sensible to think about quantum dot technology. So Samsung is making displays that cost only a little more than, on a per square meter basis, than photovoltaic modules that use quantum dots. So the other feature are these highly luminescent 3-5, in this case, indium gallium phosphide solar cells. These are little hundreds of square microns microcells, and they're connected by a wiring network, and they're embedded inside the polymer encapsulant. So this is the only difference between this and a normal silicon photovoltaic panel, which has that polymer encapsulant right there, is that it has embedded in that polymer encapsulant quantum dots and these small solar cells. And there's another very special thing. It has mirrors on the front and the top that have very special properties that I'll tell you about in a minute. So the concept here is that the quantum dots absorb the blue part of the spectrum. Then there's a so-called downshift or Stokes shift of the luminescence emission relative to the absorption. That is the key to the thermodynamic basis for concentration. I'll tell you about that in a minute. That emission is now matched to the band gap of this indium gallium phosphide solar cell, which is shown in the orange. So this photon energy is just above the band edge and is efficiently absorbed in these small solar cells. So the scheme here is light comes in, is trapped inside this waveguide, trapped by the mirrors, absorbed by the quantum dots, re-emitted luminescence radiation, very similar to the process I described in gallium arsenide, but now inside a polymer waveguide, and then is absorbed by the indium gallium phosphide solar cells. And if the area over which the light is gathered that is collected by this solar cell is greater than 1, that represents concentration. And I'll show you in a minute that we can get to rather high concentration numbers. So we're interested, of course, in making photovoltaic modules that can exceed the 30% efficiency range. So we need to have quantum dots that are highly luminescent. The Stokes ratio, which is the ratio of absorption to emission at this luminescence wavelength, should be a factor of 50. That's just sort of a matter of how well you can engineer the ensemble of absorption of an ensemble of quantum dots. We need mirrors that have a very funny characteristic. that they are perfectly reflecting at this wavelength and they are perfectly transmissive at all other wavelengths. But I'll show you we can do that. And so this is what they look like. And so Frank told me if I push the fourth button, I've got it. You can see here in ordinary light in the lab, you can see this waveguide is glowing an orange color. That is the glow of the quantum dots emitting at this wavelength here at 630 nanometers. So under ordinary room light, this highly luminescent material is glowing. So this is the top mirror, this is the polymer waveguide with the quantum dots, with the embedded microcells, and these tabs are coming off a commercial Jinko solar technology, silicon solar cell. So the basic picture of this is that in a quantum dot or in a luminescent solar concentrator, we pay an energy to reduce the entropy. So the idea is a local or closed thermodynamic system. If I lower the enthalpy, I'm also entitled to lower the entropy. And so we know, for example, for just ordinary scattered light, that it's exceedingly unlikely that the light coming out of my laser pointer would ever be easily reversed. That it's very unlikely that we'd have a scattering process that would result in the light scattered from the screen coming all back into the laser pointer. That's the expression of entropy, right? The entropy, thermodynamic losses due to entropy. However, if we pay and what we can show thermodynamically is that by downshifting the emitted photon energy, we can reduce the entropy in the waveguide. In fact, this was expressed first by Eli Jablonovich and actually by a fellow named von Rusbeck and ultimately Shockley. Our good friend Shockley played a role in this, who pointed out that the concentration you can get associated with the downshifting of the photon from its absorption to its emission goes in a geometric factor of the ratio of the energies to an exponential in the energy difference between the absorption and the emission. So you get an exponential concentration factor. So if you could now make something where the downshift was a few hundred millivolts in Stokes shift, in principle, if the luminescence efficiency was high, you could make concentration factors of not only 10, 100, 1,000, 10,000. You could even go beyond the ray optic thermodynamic limit for light for geometrical optics, which is a kind of a crazy idea. But thermodynamics does not disallow this. It's quite interesting. The problem is right now the luminescence efficiency and the light trapping characteristics have limited us so far to concentration factors in the range of 5 to maybe 10. And so this is what we're trying to change. And this von Rusbeck and Shockley basically worked out the physics of this that basically showed that this exponential decay in the absorption corresponds to an exponential increase in the concentration factor for luminescence photons that are downshifted by an energy delta E from the band edge. So then what we want to do is make a mirror that traps these photons inside the waveguide at this wavelength, but allows us to absorb above the band gap of the quantum dot. So that's the name of the game here. So if we now make one of these waveguides that has quantum dots in it, and the quantum dots absorb light and then they emit luminescence photons, but we all know that total internal reflection can happen, and at angles smaller than the angle for total internal reflection inside a glass or a polymer, some of the light would escape. And in fact, if that happens, we lose some of the photons and that degrades our concentration factor. So even if we have a large area, say ratio of the collection area to the cell area is a factor of 40, we only get a concentration from a factor of 5 because luminescence photons are escaping from the waveguide. If we do something clever and we have very high luminescence efficiency and we have total internal reflection, we could do a little bit better. And if we had a very nice light trapping structure, we could actually make the concentration factor follow the geometric gain. In other words, the ratio of the energy absorption collection area to the ratio of the small solar cell. So that's the goal. How high can we make this number? So historically, I won't go into this in detail, people began work on this back in the mid-1970s, during the first energy crisis, and they were using organic dyes. And that was a sensible thing to do at the time. We didn't have quantum dot technology. But the organic dyes had luminescence efficiencies that were at most maybe 60 or 70%, and they were quenched relatively easily. So we were never able to get concentration factors that could go more than about a factor of 5 or 10. So more recently, we've been able to work, we're working closely with my good friend Paul Alivisatos in Berkeley, who is one of the pioneers, of course, in quantum dot technology. And we can now, and when I say we mean we can emulate the process developed and pioneered in his lab to make quantum dots that are indistinguishable in terms of the measurement error from 100% luminescence. It's less than 100%. We just can't, we don't have, at the moment, accurate enough measurement techniques. In fact, right now, one of the things we're working on hardest is new, better techniques for luminescence measurement, actually. But anyway, we know now that the luminescence quantum yields, the radiative efficiency, can be greater than 99%. We have some of the world's best indium gallium phosphide solar cells. They're made by John Geiss at NREL. And this is the nice luminescence coming from the solar cell superimposed on their absorption spectrum. Now, if we use such structures in a waveguide structure with an open waveguide, in other words, no mirror on top to recycle photons, we have this same purgatory of low concentration and high geometric gain. But if we now put this spectrally selective mirror here, we can see that the concentration factor keeps going up linearly, so that's very encouraging. And if we work on more optimally designed mirrors, and this is a mirror that has a reflectivity of 99.99%, it's a simple Bragg reflector, but that's an illustration of how effective Bragg reflectors can be. But the other thing that's interesting is this Bragg reflector has about a 3 or 4% reflectance out of band, where you don't want it to reflect. And as a result, we've been able to get to a record efficiency now almost 40 times. And so we're now in the range where this flat sheet can concentrate diffuse sunlight in a flat panel by a factor of 40x onto these small solar cells. So now arguably I could work and be cost competitive in the range where these solar cells would be 40 times more expensive than silicon on a flat plate basis. So that's kind of the kind of thing that we're thinking about. So I want to shift gears a little bit and talk about new materials. This is you are all material scientists, and I've been telling you some wonderful things about photons and optical engineering and the thermodynamic basis. So if you go away with any feeling today, it's maybe that somehow thermodynamics has something to do with light and energy, and that's the main impression I want to leave you with. But I want to also mention that there are exciting opportunities over the horizon. I mentioned there are new materials that people are working with, perovskites. These look promising for thin film photovoltaics, but the promise is tempered by the challenges associated with the instabilities, the environmental instabilities. As Roger will tell you, they're shockingly unstable relative to silicon solar cells. So the question is there any material that could be simultaneously abundant, cheap, and stable that you could use in a thin film solution processable solar cell form? And recently, in the last few years, people have been working on these marvelous two-dimensional materials, which have been around for a long time, but they've been recently recognized as bona fide electronic materials or optoelectronic materials, and they have fascinating properties. These two-dimensional sheets of chalcogenides like molybdenum disulfide effectively have the same molecular precision that we have in small molecules and polymers. They have perfect structures, aside from the inevitable defects that we like to study, on the surfaces top and bottom, the so-called basal planes. So if we can make large crystals or functionalized edges, then we can make materials that have very interesting properties. It turns out that in their monolayer form, they form direct bandgap semiconductors, and I'll show you in a minute, they have very, very high luminescence efficiency. If you make them multi-layer, they're indirect bandgap semiconductors, but they're actually in the right bandgap range for use in photovoltaics. So these are quite interesting. And one of the things, features that because these are van der Waal heterostructures, we don't have to worry inherently about the lattice matching that we would in covalently bonded semiconductor materials. So we can think about making heterostructures where we combine things like different chalcogenide semiconductors like molybdenum disulfide, tungsten diselenide, and say conductors like graphene. So a very exciting development that came from the lab of Ali Jaffe about a year and a half ago was the recognition that by chemical functionalization of the few defects on the basal plane of molybdenum disulfide, we could make the luminescence quantum yield be close to 100%. This is as luminescent as gallium arsenide or as perovskites. This is a shocking development. This is my first exposure to molybdenum disulfide. When I started at Caltech, I built an ultra-high vacuum system for doing experiments, was as a galling grease. It's a non-hydrocarbon lubricant that you could lubricate the bolts on your stainless steel vacuum chamber. So this is galling grease that has luminescence yield of 100%. It also, among semiconductors, it's the most highly absorbing of any of the semiconductors, at least that we've been able to gather data for. It's more highly absorbing than gallium arsenide, perovskites, and in single layer form, or any of the organic semiconductors. So on a per layer or per atom basis, it's very highly absorbing. So the question is, can we do something interesting? Well, we've been able, and many others now have followed in growth of materials by chemical vapor deposition. We can make this on a wafer scale. But it's also interesting to note that there is sort of a bucket chemistry version of this as well. You can actually chemically exfoliate, just like we made the galling grease, and make layers and functionalize these layers. So I think there's a cautious reason for optimism that we could make a solution processable solar cell technology using this metal dichalcogenides. So as usual, the kinds of things that we want to do in photovoltaics are to absorb all the light, collect all the carriers, and maximize the voltage. Sounds simple, and I probably convinced you that in gallium arsenide it is simple. In any new material, these are the challenges, and they're usually not simple. But I'll show you that we've been able to make some progress against each of these objectives that you need to satisfy in order to make a high efficiency solar cell. So I'll first talk about the light absorption. And so of course we're now dealing with films that are a few monolayers thick. So how can we possibly make them be sufficiently light absorbing? Well, they are very light absorbing on a per monolayer basis, but let's see how good they can be. Well, so you don't even have to do any spectroscopy to get the answer. All you have to do is use your eyeball spectroscopy. So this is now an example. So if we look at a few, this is a 13 nanometer layer of molybdenum disulfide sitting on a silver mirror. And what is the first thing you notice about it? It's black. It should be transparent if it's a very thin material, right? And it's not. And what we're seeing is actually a resonant interference condition that is built up at special thicknesses here, where we can get very high absorption, and we can see broadband absorption, more than 80% in layers that are less than about 20 nanometers thick. And so this is some transfer matrix calculations showing as a function of thickness, absorption here from 1.5 nanometers up to 20 nanometers, and these are the experimental. And you can see we get to pretty close to bulk absorption when we get above about 15 nanometers. And so this is also angle independent. If I now look at the spectrum as a function of angle, you can see if I had some structure like a diffraction grating, it would be very, very angle insensitive. I can go to an angle of 60 degrees, and then finally I'm just losing due to the cosine losses in absorption. So it's very, very angle insensitive, this absorption enhancement. So then let's try to make a solar cell. So we're going to make a solar cell by making a solar cell between two semiconductors. Tungsten diselenide is known to be native p-type. We think due to tungsten vacancies in the structure that render it p-type. Molybdenum disulfide is known to be native n-type, probably due to the sulfur vacancies in the basal plane, which act as donors. And this forms a type 2 heterojunction. There's a type 2 PN heterojunction. And then we're going to put a layer of monolayer of graphene on top to act as a transparent conductor. And this is a structure that was made by a Scotch tape method rather than CVD method, so we could isolate and build up layer by layer with the contact. So it's rather small. It's about 100 microns across here. And this is a photocurrent map, of collected photocurrent map. So you can see here that the internal quantum efficiency is about 70%. It's not 90% like it was in gallium arsenide, but it's still pretty good. And when we got into the game, the records were around 15%. So we were able to show that we can not only have high absorption, but high carrier collection. In fact, the reason that you have high carrier collection remains to me very much of a mystery, because all that we know about the electronic structure of these layered van der Waals materials suggests that you should not have very facile charge transport perpendicular to the planes. You should have high mobility in plane. So we think this might be defect mediated, but this is an active area of research at the moment. So the other thing we want to do is to now create the proper conditions for achieving high voltage. And previous to our work, the voltage records were about 200 millivolts for voltages in chalcogenide materials. But of course, everything we know suggests that what we want to do is to have carefully band-aligned materials. So what we know is we want to have selective contacts to selectively extract the holes or the electrons. So we searched through essentially the entire database of materials that have been studied for thin film solar cells and did photoemission spectroscopy we measured the band offsets by photoelectron spectroscopy and found the work functions for nickel oxide and titanium oxide, and we're able to identify these as being materials. We looked at many other materials as well, I won't tell you about in detail. But by choosing these in such a way that here nickel oxide blocks electrons but collects holes, titanium oxide blocks holes but collects electrons, you can see they're not perfect according to this, because a perfect material would have its conduction band aligned with the conduction band of the semiconductor, and nickel oxide aligned with the valence band of the semiconductor. But they're relatively good, and that enabled us to get to a record voltage of about 700 millivolts so that's not quite as where it needs to be, but it indicates that this is the arrow, the direction arrow for progress at least. So at this point, we've been able to get to the point where we can make highly absorbing films, relatively respectable internal quantum efficiency, some work to go on the voltage. We should be able to get to about 1100 millivolts or so, but we think that with more optimal and essentially mining the treasure chest of other thin film photovoltaics using the principles of correct band alignment, that we can probably do that. So I want to finish now telling you about generation of fuels. And so at the reception we had just before the talk, there were some nice comestibles to go along with the drinks. And so and maybe some of you this morning had something that looked like this, Winchell's or Dunkin' Donuts or something like that. I had something that looked like this from Starbucks. It costs a lot more than that, but anyway, let's do an energy analysis, and I'm going to ask you to grant me the conceit of interconversion efficiency between electrons and chemical bonds for the moment. We'll get back to that in a minute. But let's think about the energy density that's intrinsic to this versus this. So, okay, we know that this has about 400 calories if you look on the health and nutrition information at Winchell's Donuts. That means to a scientist 400 kilocalories, or about 1.7 megajoules if you're an MKS person. And so that means that I could then extract about 460 watt hours if I were able to convert the chemical bond energy in this glazed donut to electrical energy. So for batteries, the battery density or battery capacity that I would need to achieve 450 watt hours looks like this. So this illustrates the power of chemical bonds. In this device, we store energy chemically, but we have to carry around the oxidizer, the fuel, the electrode infrastructure, and everything, and it gets heavy. You have these cobalt atoms and things like that, and oxygen. Whereas here, we can convert this to things like hydrogen and methane and so forth. And so it's the energy density is really quite spectacular, and that's why we use fossil fuels in internal combustion engines in conventionally fueled vehicles. And that's why it's so hard to make transportation be powered other ways. So in artificial photosynthesis, what is artificial photosynthesis? Artificial photosynthesis is an enterprise for converting chemical fuels into sunlight that emulates nature's example. So if we think about how, for example, chlorophyll works in a photosynthetic system in the leaf of a plant, we have two light harvesting centers. We have photosystem 1 and photosystem 2. photosystem 1 acts to generate protons by a water oxidation process, but the excited charge carriers, it generates 4 electrons, that's important, and that in these excited electrons are now transferred to photosystem 2. These are close in spectral position, 680 nanometers, 700 nanometers in the red. That's why the scattered light from your plants looks green. And so this second, the P700 system now excites again with another 4 photons and excites these 4 electrons up to the point where in a dark reaction center they can generate NADPH. NADPH is the precursor together with ATP to generate ATP and to create the starch and sugar that is needed for the sustenance and livelihood of the plant. Okay, so this actually is a tandem solar photovoltaic energy generation process. It looks a lot like a tandem dual junction solar cell. In fact, it's just using tandem photon absorption at 2 wavelengths. So in an artificial photosynthesis structure, we're interested in now creating an anode. That anode has an oxygen evolution catalyst that produces protons, and in the case of water splitting, a hydrogen evolution catalyst. In the case of CO2 reduction, we'll use a different catalyst for reducing CO2. And this tandem photovoltaic structure has to overcome the thermodynamic potential plus the kinetic overpotentials for the reaction, say in this case the water splitting reaction. The thermodynamic potential is 1.23 volts for water splitting. We were talking about this earlier today, that if you, Frank, that in the corrosion process, if you turn up the voltage on your hardened alloys and go past the 1.2 volts, you actually start to split water. To do it at finite current densities, we also have to go a little higher in voltage because of the finite turnover frequencies of the catalyst. When I wear my engineering hat, I like to think of the turnover frequency of the catalyst as effectively a contact resistance. It's due to the finite rate at which you can take charges and turn them into reduced or oxidized species. So now we're going to combine 2 semiconductor materials in a tandem photoelectrode, oxygen evolution catalyst, hydrogen evolution catalyst. And in this process, to generate hydrogen, we use 2 photons, or in hydrocarbons, anywhere from 6 to 12 or more photons to generate chemical fuel products. And so these are the reactions. The hydrogen evolution reaction that takes electrons that transit the same path as the protons, which come around to the other side through a membrane, and combined with the protons generated by water oxidation to produce hydrogen. So the first fuel we can make is hydrogen just by splitting of water. We use a water electrolyte. If we now add CO2 into this electrolyte or into another medium up to the solubility limit of CO2 in that medium, we can generate other reduced products of CO2, including formate, alcohols, methane, and other alkanes. So this organization, JCAP, which is the Solar Fuels Energy Innovation Hub, this is one of the energy innovation hubs that was started under the leadership of Secretary of Energy Steve Chu when he was Secretary of Energy, as a cross-cutting center to advance energy technology and science. And in this case, through artificial photosynthesis, and our first goal was aimed at water splitting. And so this was a process that aimed at combining discovery science, so discovery of new materials, new, say, complex oxides that act as photoanodes for water oxidation. Discovery aided by a high throughput experimentation process. We use combinatorial synthesis, very much like drug discovery. We use plates that are very much like the microarray plates that are used in drug discovery. This is literally, if you look at the dots there, every one of those little dots is a complex metal oxide that was inkjet printed from an inkjet printer from a metal ink and calcined in a furnace to make a metal oxide. And then a scanning measurement device made an electrochemical measurement on each of the several thousand alloys. And so this is really, you can see very visually how you can accelerate materials discovery. We also require polymer membranes to separate and transport protons and anions, but block the product gases like hydrogen or methane. And of course, in order to understand what the role of the materials, we need to use in situ and operando spectroscopy to understand the energy and the structure of catalysts. And we also, as we accumulate knowledge base, a database about catalysts, we benchmark them by their overpotentials required to achieve catalytic action at a given current density. And then finally, JCAP has worked on development of prototype devices. When we started the program, we didn't really even have a good conceptual idea of what a solar fueled generator looked like. And now we have devices about the size of a laptop that are electrochemical cells that I'll show you in a minute that are prototype water splitting devices. So just to illustrate the power of materials discovery, this is a combined combinatorial high throughput theory and experiment effort. It's not high throughput experiment only and a little bit of theory, or high throughput theory and a little bit of experiment. It's high throughput both. We use the database of the materials project where the PBE density functional theory, PBE level density functional theory, band gaps and other electronic structure parameters have been computed for many thousands of materials. And in this case, we're interested in transition metal oxides, chromium, manganese, copper, and vanadium-based ternary oxides. And we're starting with about 3,000 candidates. These were screened using the band gap calculations at the PBE level and phase stability. From the electronic structure, we were able to derive effectively the Pourbet diagrams that indicate the electrochemical stability at a given pH. And from those, we were able to reduce down to screen down to a few hundred candidates. Then we used the hybrid functional method to make more accurate band gap calculations that are much more accurate for oxide materials and mixed valence materials to derive the band edge. And then finally, we tested experimentally a number of these materials, looking at their stability in water and their band edge energies. And so this illustrates sort of the process. And so some of the results have been materials like this, like copper and vanadium oxide, copper vanadate, in a number of phases that were only known to geologists before. In fact, they have geology-sounding names like fingerite, McBurneyite, zeite, and blossite. And now we can know them to be useful electrochemical materials because they have appropriate band gaps and their band edges straddle the water oxidation and water reduction levels. So therefore, we can transfer charges from the conduction band to the catalyst efficiently here, both on the water oxidation and the water reduction side. So this is this kind of virtuous circle between theory and experiment is a powerful one that we're exploiting for water oxidation, water reduction, protective coatings to prevent corrosion. And so it's quite a, and so this is just one more point on this, is that we were able to show from a different screen on a wider variety of complex oxide-based photoanodes, starting with more than 60,000 compounds. We were able to go down using theory in blue and then experimental screens in red to get 15 hits, meaning 15 candidates that had the correct band gap, were electrochemically stable, and exhibited signs of water oxidation. 3 of the 15 were already known compounds. In fact, they were the only 3 compounds that were known. But we discovered 12 new ones. So we expanded by a factor of 4 in this one experiment the number of known compounds that satisfy the set of criteria as workable photoanodes. So that culminated in a number of prototype devices, and this is some of the JCAP researchers that were instrumental in building one of the first stable, efficient, and by efficient we refer to devices that have efficiencies over 10%, water splitting efficiency, that's photons in, molecular hydrogen out. They feature oxides, doped titanium oxide layers that protect the intrinsically unstable 3,5 semiconductor photoelectrodes. They have earth-abundant electrocatalysts, and they use anion exchange membranes to pass hydroxyl from across from the cathode to the anode side. And so this kind of device, this is the obligatory what we call bubble video. If you look closely here, you'll see bubbles of oxygen here. This is a photoanode under solar illumination. And if you do chromatography, GC measurements, you see a 2-to-1 ratio of hydrogen to oxygen, indicating 100% Faradaic yield on the current for water splitting using nickel molybdenum nickel oxide catalysts. Okay, so that's interesting. We made prototypes of the size of a laptop in the lab. Could this ever scale? So we did an analysis of what would happen if you built a 1 gigawatt hydrogen plant using this kind of technology, notionally located somewhere in the desert between Los Angeles and San Francisco. You have plenty of sunlight, you're near urban centers, you have some infrastructure to pipe into, a pipeline network. But we went through a whole techno-economic analysis and said, okay, well, let's not only think about what it takes to make the device, but let's think about what it takes to put them into shipping containers, put them onto trucks, deploy them in a field, pay for the piping, the compression of the gases, the stainless steel tanks, the whole 9 yards. And so we actually spec'd out in this paper a whole analysis of this gigawatt structure. And the good news is it has an energy return on energy invested. That was the metric used, not financial return, greater than 1. And it would have been depressing if it were less than 1. And in fact, the factors that are most leveraging in determining how much bigger than 1 you can, by the way, the payback time for the device I showed you in the prototype, if you directly took that first generation device and did this, would be about 8.5 years. So if we could make the device last 30 years, that would be interesting, because I need to talk to Roger about this. But the factors that we're most leveraging on the economic return and the energy return are the efficiency and the lifetime. That's good news for researchers. Those are the things we like to work on. It would have been depressing if it were the cost of stainless steel pipes and tanks, right? Because that's not something that we can do much about in the most case. So a lot of the balance of system costs were less important than the direct component technology for energy conversion. So more recently, we've been able to, and this is a paper on arXiv, get close to 20% water splitting efficiency. So this is, I told you at the beginning that the commercial photovoltaic panel conversion efficiency is about 20% now. So we can now, we're close to 20% in solar to hydrogen efficiency for record prototype small devices. But I think it's reasonable to expect that in the next few years we'll see solar water splitting driven devices that have efficiencies for generation of hydrogen that are comparable to photovoltaic panel efficiencies and cell efficiencies. So this is accomplished by making anti-reflection coatings that are catalytically active and align the band edges of the catalyst with the conduction band of the semiconductor, and effectively act as an anti-reflection coating under the water. So a number of things that are, so this is now getting to a relatively sophisticated level of device technology with a lot of deep material science inputs into it as well. And what we're seeing in the last few years is a rapid increase. So from 2015 up to 2018, we've seen a rise from 10% up to 14 to 16 to 19% efficiency. So we're really in a golden age for prototype development now. And interestingly, if you compute an equivalent Shockley-Queisser limiting efficiency for water splitting, we're currently at, for the band gaps of the semiconductors used in this dual junction absorber, we're at 85% of the entitled Shockley-Queisser efficiency. So which is quite, it tells you that we're getting, we're learning what are the features that are most important. Okay, so I want to say just in the last 2 minutes or so something about carbon dioxide. Of course, the world's biggest challenge is with trying to reconcile our energy use with ever-expanding emissions of greenhouse gases. So the current phase of JCAP is aimed at closing this cycle, doing carbon transformations on CO2 that would enable us to generate useful fuels and chemicals. So our targets are to combine CO2, solar energy, and water to make fuels and chemicals, alkanes, alkenes, and primary alcohols. So if you wanted to take CO2, which is currently being generated worldwide at a rate of 10 gigatons per year, and you asked, where would I put it? What industrial processes could I put it into? The answer is that almost unavoidably it has to be fuels and materials. Coal, oil, and gas, we want to displace these fuels, these hydrocarbon fuels. Materials like cement and carbon-based substitutes of structural materials as carbon-based substitutes for steel, composites. So these would be remunerative, perhaps money-making products that we could make where we could derive some economic benefit from the infrastructure investment. Here, we could also sequester it, but that's pure cost. We have to have policy and subsidy to drive the cost. So right now, we already have Fischer-Tropsch processes, and we have water-gas shift reaction. We could take carbon monoxide and hydrogen, and we could build a plant like this. This is a Fischer-Tropsch pilot plant in Japan. As you can see, it has a relatively high capital cost. To my way of thinking, it would be much more elegant to make something that looks like a photovoltaic module and has a similar cost basis that performs this function of producing the reduced products directly under mild temperature and pressure conditions. There are many ways to do this. I won't tell you about all these. That JCAP is focused on electrocatalysis and photocatalysis. There are very exciting things going on in biocatalysis. And in industry, people are most optimistic about using thermal methods, which of course are used in the downstream chemical industry extensively. So JCAP focuses on these two methods. And at the moment, I'll just go to give you a quick status update that our best catalyst for reducing CO2 to products beyond carbon monoxide or methanol is copper. Copper in its many forms produces many products that we can see, and so we've begun a very intensive study at both the theory and experimental level at the atomic scale under operating conditions, under in situ and operando conditions of the atomic scale structure and the dramatic rearrangements of the atomic scale structure of copper under electrolyte working conditions, because that is the key to developing these as active catalysts. We have a variety of strategies of combining multiple surface sites and alloys, making nanoscale confining structures that are a few angstrom scale crevices, tethering molecules to surfaces, engineering the electrolyte, the buffer ions in the electrolyte, generating atomic scale ledge sites that are under and over coordinated to increase catalytic activity. We have a parallel effort using understanding how the excited states of light, excited electron hole pairs in both metals and semiconductors, can be used to generate efficient photocatalysts as well. So there's a lot of work going on in the theory that's focused on understanding how to describe the kinetics, to screen catalysts, and also to develop understanding of the liquid interface. It turns out one of the materials that has most widely eluded scientific understanding is water. And it's a real challenge. On the catalyst side, we're looking using experimental methods to discover new catalyst compositions, look at the atomic scale structure, and to control the morphology, to design reactors, to make prototypes for CO2 reduction like the ones I showed you for water splitting using these very nice beamline tools. Finally, I'll just show you one scientific highlight that's very exciting. We've identified, this is from the lab of Teo Agapi at Caltech, who identified a pyridinium which forms a polymer, condenses to form a polymeric film on copper electrodes that produces, under electrocatalytic conditions, 80% ethylene and ethanol, and suppresses water splitting, despite the fact that water is ubiquitous in the electrolyte, suppresses water splitting down to a few percent. So this is really an indication that I think we can make fuels and chemicals, ethylene of course being the precursor to polyethylene plastics, and ethanol already being a useful fuel, and we think we have a chemical understanding to how to develop tandem pathways to go to propanol. So in essence, the opportunity is to use solar-driven electro and photocatalysis to fill out this landscape, a sustainable energy landscape that features baseload power generation with renewable sources, taking the CO2, for example, and recycling it, generating hydrogen, generating carbon-containing chemical fuels in this entire ecology. And really, being able to develop these as a base technology for the next generation, I think are keys to making this sustainable landscape become a reality. And so I'll finally finish by consulting another philosopher known to us as America's greatest inventor, the founder of General Electric, Thomas Edison, who in a conversation with these guys, Henry Ford and Harvey Firestone, you may believe had something to do with the auto business, in 1931, mind you, he said this: "We're like tenant farmers, chopping down the fence around our house for fuel when we should be using nature's inexhaustible sources of energy, sun, wind, and tide. I'd put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until all the oil and coal run out before we tackle that." So thanks very much.
So I expect that there'll be a few questions and things like that. Who would like to start?
Roger, Harry, the rate of improvement in silicon efficiency, can you spend a little time explaining what the cuts of that involve?
Well, so silicon is now reaching its zenith, I would say, and the efficiency has to do with, and in fact I can go back and consult this taxonomy of different semiconductor materials that I showed in the beginning, just to sort of know where we are on the landscape right here, and note that this we're not at I would say a state of optimized performance for silicon. There's still a little ways to go on the voltage. It's pretty close to collecting all the current it can collect. And I would attribute this just to the fact that we've made now billions of solar cells in silicon. And we haven't made billions of solar cells with any other material. And the cumulative cycles of learning, but it's all those processes that I talked about with regard to the molybdenum chalcogenides, absorbing the sunlight, efficiently extracting the carriers, and maximizing the voltage. People have learned how to do this in silicon exceedingly well. And remarkably, they've also learned how to do it with crystal growth, of materials that now have recombination lifetimes of carriers in the millisecond range at the ton scale in big plants, things that I would have never guessed to be possible. It's really quite a remarkable story. It's not attributable to any one person. It's the cumulative efforts of a huge group of people. So it's quite a remarkable story.
But then it's also even surprising, like in silicon, that PERC modules and PERC cells now come along with this kind of 10% increase in efficiency. They were known in the 90s.
So in fact, one of the pioneers in this field is a fellow named Martin Green in the University of New South Wales in Australia. And the basic solar cell technologies had actually been invented about 25 or 30 years ago. But we didn't know how to solve some of the parasitic recombination problems. A lot of them were material science problems that were addressed along the way. Our sophistication of understanding the current modern analytic methods we have, all of those play a big role. I think that's a lesson for any other incipient technology that you might think about developing, like solar fuels, that you really don't want to combine this entire modern arsenal we have of R&D and methods in the development process.
So in that map right there, where do you think the perovskites have their headroom going? They've been increasing in efficiency, not in stability, but can they get over to the blue area?
I think that if we were to design perovskite solar cells with the same level of thoughtful design that we did for gallium arsenide, we would be able to get the voltage over to here. Yeah, I don't know about the current. Yeah, but yeah, I think so. Yeah.
So you mentioned that to make a good solar cell, you also need to be a sort of a good LED. And I've also heard Eli Robic talk about that recently. So what was the key to making a better LED actually? What processes of losses and so on do you have to avoid? And And some of the most efficient LEDs we use now are nitride. So does that mean nitrides have a chance in the solar game?
That's a
or
very interesting
will
question.
their gap
Yeah.
just be big for being useful in the...
Yeah,
in this?
that's a very interesting question, actually. Well, sometimes you have to accept the gifts that nature gives you, which it did with gallium arsenide, and which it has done with the perovskites. These are materials that have remarkably... So I think from a semiconductor physics point of view, the thing that you want to avoid is electronic defects that lie within the center of the band gap. Those electronic defects that lie within the center of the band gap tend to be non-radiative and drive very high rates of non-radiative recombination. The perovskites, for example, are incredibly disordered materials. They're practically liquid-like in their structure. But remarkably, the defect states are all concentrated near the band edges. There's a remarkable lack of defects in the center of the band gap, and so it can support very high radiative and low non-radiative. So if you're starting from the point of view of materials design, that would be one of the most important criteria I would lay out. Try to design things that don't produce a lot of defects right in the middle of the band gap. So you asked about gallium nitride. So gallium nitride by itself has achieved very high radiative efficiencies. The challenge is that the gap is quite wide. We can alloy with indium, for example, to bring the gap down. So far, when you do that and you bring the radiative efficiency doesn't hold up quite as well when you get it down into the range where it's useful for. So I think the jury is out. I think it could be that it may come to be useful. Certainly, we're going to see, I think, nitride LEDs on our phones. Actually, one of my students went to work for Apple, and he refused to tell me what he was working on, but I figured it out anyway. And it's visible nitride LED microdisplays. So I think we're going to see, hopefully, that technology for very high radiative efficiency, gallium nitride driven even further. Yeah.
So thank you for a really wonderful talk. In terms of the sort of overall energy picture that you described, that there was a lot of chemistry being fueled by solar energy to produce things that were stored and that you don't have to cycle. Do you think in that balance of things then that the grid wouldn't need to be changed much in terms of overall design, because if it's all solar and then there needs to be a massive overhaul, right? If there's storage, then so where do you see that?
Well, that's an interesting question. When Steve Chu first became Secretary of Energy, I talked to him a few weeks ago when I was up at Stanford. So the question is, how do we get to this picture, of the renewable landscape? Steve, when he first came in as Secretary of Energy, he was filled with enthusiasm to completely rewire the American electricity grid. Actually, the American grid is 3 grids. There's the Eastern grid, the Western grid, and then Texas, which has its own grid, independent. And they did a cost estimate through the Congressional Research Office, and it was going to cost $1 trillion. And nobody in government was willing to spend $1 trillion on it. So I think the reality is we're going to have to figure out ways to iteratively move forward using the kinds of innovations that the private sector is generating that cost less than $1 trillion to incrementally adopt.
Ari, I have a question regarding your cartoon about the design, the new physics of the photovoltaics that you showed in the very beginning, where you created a sort of cavity to have these cathode photons inside, right? So, and I was waiting to see, the special mirrors that you were using.
Oh, okay, yeah.
And also, in that cartoon, it seems to me that you want to use the whole idea of EI to speed up the spontaneous emission.
Oh yeah, that would be a great idea. This solar absorber in the actual commercial solar cell is thick enough that it's hard to design. And yes, I agree completely. I don't want to disagree with that. I was giving, and in fact, in essence, this is what there is a small effect here. It's not one. You're absolutely right that so what Professor Strongy is referring to is the fact that in a structure where I can change the optical density of modes, I can change the balance between radiative and non-radiative emission by controlling the number of emission channels. That's real nanophotonic engineering. And I think in thinner structures, there's a real opportunity to do that, like the chalcogenide cells that I described earlier, where you have very strong, for example, plasmonic modes and very thin film dielectric modes. And we have seen changes in the radiative lifetime in those materials. Yeah. Yeah.
So we need some questions from students.
In one of the samples you passed around, I believe it was the lava one, they were sort of stacked like shingles. Is that how the cells connect to each other?
Well, if you think about if you had to passively connect cells in a way that was the most robust method, you would want to construct them in a sort of combined serial and parallel network, right? Serial allows you to build voltage. That's always useful in a photovoltaic module because you don't want to have high currents, because then you get ohmic losses through the metal wires. But you also don't want to have them all in series, because then you have the Christmas tree light problem, right? If you have one open circuit, it makes your whole device be unreliable. Making this whole series parallel connection in the sort of brick-like architecture allows you to get sort of not an optimal, but a good trade-off between those two requirements.
So I've been looking a lot at anti-reflective coatings, and typically we talk about different aspects. I've been kind of looking at the ones that distribute the light, and then you get the increased efficiency from having light kind of open at the same angle. And these newer studies that you're talking about, where there's the light's trapped inside of a cavity effect, or you have the waveguide effect. Is that still an advantage, not have the light come in one direction, that angular dispersion, or is that kind of overcome by the engineering design?
So it's always desirable to be able to accept light with angle insensitivity, because most solar panels are deployed in places where it's cloudy. I'll just say that hands down. They're not deployed in places where the sun is like a laser. So as a result, it's always best to have a wide acceptance angle. And so fortunately, we have some designs that meet that criteria of acting as good anti-reflection and sort of what we call over-damped or low Q cavities that have a relatively wide acceptance angle.
So I think for that we should actually let Frank come up to present the Van Horn Award.
So yes, there's one final pleasant part to this first lecture, which is this plaque for you, Harry, which hopefully is correctly filled out, and I think it is. And there's also a check related to this award.
Thank you.
So let me congratulate you on this.
Thank you.
And thank you very much for this wonderful presentation. We highly appreciate it.
Okay.